Hello, welcome back. We're talking about Chapter 3 now, or 3.1 is exponential functions. Now Chapter 3 is all about exponentials and logs, so yes, you guessed it, we're going to hit them eventually, but we're not there yet. So anyway, we're going to be graphing exponential functions, solving exponential equations, and using exponential formulas to solve word problems. Alright, so for exponential functions in general, as a basic definition, it's a function in the form f of x equals a to the x, where a can't be 1 and a is greater than 0. Well, a is greater than 0 because we don't want to have a negative number to a power, because actually when you start using exponents, depending on the exponent you use, you might be implying a root of some sort, and then all of a sudden you're taking roots of negatives, and that's bad. The a is not equal to 1, of course, because if I take 1 to various powers, I just get 1 the whole time. So basically a can't be 1 because that would be just boring. So let's start going. Alright, let's take a look at the graphs of some of these exponential functions, because of course if you have a picture in your head of what these things look like, and hopefully it'll help you understand how these things behave. Okay, so anyway, let's go with this. With the x, I'm going to run some exponents, because that's what the exponent is right there, the x. Run from 4, 3, 2, 1, 0, and then I'll run it down to -4 as well. Okay, and that's going to give us 9 points. Hopefully that gives us a really good idea what this thing's going to look like. Okay, as I plug in a 4 here, 2 to the 4th, that's 2 times 2 times 2 times 2, which works out to be 16. Plugging in a 3 gives me an 8, 2 gives me a 4, 1 gives me a 2, etc. I get a 1 there. Okay, now, hopefully you remember a negative exponent just means reciprocal. Or on the flip side of this, just think of how we're dividing by 2 each step of the way. So either way, that should give you a 1/2 right there. The -2 should give you a 1/4, 3 gives you a 1/8, and then 4 gives you a 1/16. Okay, if you're not sure how I'm coming up with these numbers, please do stop me and ask me in class. Okay, but anyway, as we graph these things, 0, 1 puts me right there, 1, 2, and then 2, 4, etc. And then 3, 5, 6, 7 gives an 8. 4, 16, of course, doesn't fit on the grid that I have, so let's move to the negatives now. -1 gives me a 1/2. -2 gives me a 1/4, so a little bit lower. -3 gives me a 1/8, so lower yet. And then 1/16. And I'm sure you can imagine if we keep going, I'd get a 1/32, and etc. I'd keep these smaller and smaller fractions. But I never would quite make it to 0, so that's kind of what I've got down here. Notice how an asymptote we have is going to be at y equals 0, because my y values keep getting close to 0, but we don't ever quite make it. Okay, also the domain, what's going on here with the domain, is that I could plug in any x's I want. Okay, because remember, I don't have any denominators here, and I definitely don't have any sort of roots. So the domain is going to be all reals for us. But at the same time, we have a range that isn't all reals, because notice what's going on here is I kind of have this asymptote that's kind of stopping me from going to the negatives. So my range is basically going to be y greater than 0. Of course, you could write that as interval notation if you wanted to, but I'm going to stick with the inequality for now. Alright, so as far as our graph goes, I've got that asymptote stopping me from going below the y-axis, so I'll do this guy in red so he stands out a little bit. Okay, pretend that goes horizontal with the x-axis. Alright, and then from there, connect the dots, and so it goes pretty much flat and then takes off and goes nearly vertical. Okay, he's not completely vertical because we do have other values we plug in, we just get obnoxiously large values when we do it. So there's your basic shape of these things. It's going to be kind of a J shape or a backwards L or whatever you want to think of it as, but kind of flat on one side and nearly vertical on the other. Okay, so let's take a look at what happens when we start to twist and flip this guy around. Okay, now realistically, if you have that shape in your head, you can actually get the desired effect out of a very limited XY chart. And so even though I've still got the same size XY chart here, I'm actually just going to go with 1, 0, and -1 as my X values. Okay, now you might be thinking, holy cow, what's going on there? There's a lot of stuff. Well, what I'm going to do basically here to graph one of these things by hand and to do it very accurately, I'm going to graph the unmodified version first, and then modify the XY chart to fit the various modifications that we see in the equation, and then that'll generate a new XY chart. So we're kind of going to use an XY chart for this, but I'm going to keep it as limited as possible. Because again, as long as we remember we have that basic J shape going on, we should be able to put this thing together pretty well, regardless of the base we have here, in this case a 4. Okay, well, the unmodified version of this thing is just going to be y equals 4 to the x. Okay, again, I'm ignoring the 3 and the 5 for now to just get a base starting position, and then I'll just apply what I know about shifting to change my values. Alright, that being said, if I plug a 1 in here, well, 4 to the first is 4. Again, plugging in a 0 gives me a 1 because anything. to the 0 power is 1, and then the negative 1 again just means reciprocal, so I flip the 4 over to get 1/4. Okay, so there's my basic start. Okay, so now let's play the color game here. Alright, now this x plus 3, and then I've got, let's go purple, purple's cool. And I got this minus 5. Okay, remember the number with the x is always a horizontal modification, and the number with the y is always a vertical modification, or actually the guy not with the x, but you know what I mean. Okay, so we have two things going on. This plus 3 right here is actually a shift horizontally of kind of a negative 3. So basically that's what's going on here. So what I can do is change the x column by putting in kind of a left 3 modification. So I'll do that. And then basically left 3 means I'm subtracting 3. So I simply subtract 3 from all the values I have here. If I do that, I get negative 2, negative 3, and negative 4. Okay, and then these x values no longer matter, so I'm just going to get rid of them. Okay, at the same time, we've got this minus 5 here. Okay, this minus 5 is a shift down 5. Okay, notice that's going to affect my y values, just like the left affected my x's, y, so I put it on that side. But this is going to send us down 5. Okay, well, of course, if I'm saying down 5, that means I'm subtracting 5. 4 minus 5 is going to be a negative 1. 1 minus 5 is a negative 4. And then the, brace yourself, 1/4 minus 5, and this is maybe a case where mixed numbers come in handy, that'll be negative 4 3/4. Okay, if your brain just exploded, I apologize. But anyway, that's now rendered the initial y column useless. So basically what we have here is a new x and a new y as a point. Alright, so I'm going to go with negative 2, negative 1. Negative 2, negative 1 is one of my points, which originally was the 1/4, but again, the various extra numbers in my equation change that. Okay, I've got negative 3, negative 4, so 1, 2, 3, 1, 2, 3, 4. And then I've got the negative 4, and change, so 4 over here, and then 4, and then just almost down to the negative 5. Okay, now maybe that's not enough for you to visualize right now, the J shape, but if you remember what happened originally is we had an asymptote at 0. Okay, y equals 0, that is. Okay, and our whole graph got shifted down 5, so basically our new asymptote, because of that shift down 5, is now y equals negative 5. So to stick with my color code from the previous problem, if I find that negative 5 right here, that's where my horizontal asymptote now lives. Alright, okay, so now again, hopefully now you can kind of see what's going on there with the graph a little bit better with that asymptote in place. Is we're going to smash up against the asymptote, pass through those, and notice as I do so, I start taking off in a near vertical direction, and I get myself a graph that looks roughly like that. Okay, the good news is the domain is still going to be all reals, because I can still plug in points to the left and to the right as many times as I want. And now the range, okay, notice where the asymptote is. Well, again, that puts like a bottom edge on this thing, so the range is going to be above that. So in our case now, y is greater than negative 5 for our range. Alright, so that's how you can graph one of these guys with a couple of twists and flips, but let's do one more just to make sure we got it. Alright, so this guy's got a few more bells and whistles on him, so let's take a look at what we have here. Okay, again, first of all, I want to kind of ignore all the extras on here, so really what I've got is y equals the thing to the power. Well, in this case, the thing to the power is a 1/3. So I've got y equals 1/3 of the x, and that's what I'm going to do my base xy chart from, and again, I'm just going to stick with 1, 0, and negative 1. Okay, well, 1/3 of the first is, of course, 1/3. Anything to the 0 is 1. And the negative 1, again, is just a reciprocal, effectively, so that flips him over to 3. Okay, so notice he's kind of low on the right and now high on the left. So this guy's going to be a little bit different than what we're used to. Okay, now I've got two modifications. I've got this negative 2. Okay, and again, that's a vertical change. And then I've got this plus 6, which is also a vertical change. Remember, this guy's a stretch, including a flip in our case because of the negative sign. And this guy's a shift. Well, if you think good old Aunt Sally, she would tell you to multiply first, and that's exactly what we're going to do here too. Any sort of extra flip, or two flips in the same direction, or two modifications in the same direction, x versus y, follow order of operations. Okay, so first of all, I've got that negative 2. Okay, I don't know if there's a standard notation for this, so what I just like to do is I like to say m negative 2, which to me means I'm going to multiply by negative 2. Feel free to use any sort of other notation you want to do. But of course, 1/3 times negative 2 is going to give me a negative 2/3. 1 times negative 2 is going to give me a negative 2, and of course 3 times negative 2 is negative 6. Okay. And then from there, again, that plus 6 is also affecting me in the y direction. Okay. So I'm going to now shift him up 6. So basically now I'm adding 6 onto all these values. Okay, 6 on to negative 2/3. Again, I apologize for the brains oozing out of your ear possibly, but this will be 5 1/3. Okay, 6 up from there gives me a 4, and then 6 up from negative 6 conveniently gives me a 0. Okay, now again what that has done is made these other y values useless, and now my points are 1, 5 1/3, 0, 4, etc. So now going back to graph these things, we got a 1 and then 5, 1, 2, 3, 4, 5 1/3, about right there. 0, 4, 1, 2, 3, 4 gives me here, and then negative 1, 0 puts me about right there. Okay, and again, just those 3 dots may not be enough, but I think if you get the asymptote on the graph, that'll help visualize what's going on here. Okay, and again, the asymptote normally is a 0, but I shifted up 6. So 1, 2, 3, 4, 5, 6. And again, there's now a nice horizontal line. See if I can draw that reasonably well. There we go. Okay, now again, we talked about it earlier, or at least I talked about it earlier, that this guy, because of the numbers being what they were, basically because of the fraction that I started with, this guy was actually going to be high on the left and low on the right. Okay, what we've done also with that negative sign is flipped it upside down. So hopefully those two things kind of can get together in your brain and help you see that this thing is going to go this way and flatten out. And then this guy's going to kind of take off in a vertical direction, but again, it's kind of vertically down because we flipped him upside down. Okay, I said it, but I didn't write it. My asymptote's now here at y equals 6. Again, whatever your vertical shift was, that'll be what your asymptote is now. Our domain is still going to be all reals, and yes, it'll always be all reals. And then our range, we got to be careful here. It's y. Okay, notice now he's below the asymptote, so now we're going to be talking about a less than, and the asymptote's up at 6, so y less than 6 is our asymptote there. Alrighty, well, there's a number that shows up an awful lot in these exponential things and in logs eventually as we move on later in the chapter, and it's known as the natural base e. Okay, now e, very much like pi, is an irrational number, 2.718, etc. You can see that right there. And again, just like pi, it's abbreviated by a letter. Now pi, for some reason, we said, hey, let's use a Greek letter for this one, and we decided, hey, let's use just some regular everyday number for this one. That's what happened. Anyway, basically what I want you to be able to do is make sure that you can find that button on your calculator and calculate things appropriately. So if I have to work out something like 4 times e to the negative 0.8x, and I have an x value of 7, I need to make sure that I can find a proper way to type that in my calculator. For the time sign is optional, so use it or don't. It shouldn't matter. And then, depending on your model calculator, you might have to tell the e to start an exponent here or not. It just kind of depends. But anyway, once you have that, make sure that it's indicating an exponent of some sort. I'll use that little caret symbol for it. Also, make sure, depending on your model calculator, you might have to make sure that you tell it to start the exponent and then not to stop it before you get to the 7 here. So then here, we definitely want to use a time sign for the 7 before we close it up. Okay, this is mostly the TI-8384, folks. If you have an Inspire, I think it takes care of that for you. But whatever the case, you should be able to type that in the calculator and have something like 0.01479, etc. spit out. Okay, again, since we're going to 3 decimal places, and that's really what the book is going to ask us to do, make sure you round that appropriately. So 0. Okay, 0 is your first decimal place, then you got a 1, and then a 4, because there's a 7 after it, gets rounded up to a 5. So please just make sure you can find that button on your calculator and make sure you can type things in appropriately and get the right numbers. Alright, now with e being an irrational number like it is, you might be thinking that it's next to impossible to do any sort of graphing with it by hand. Well, I'd say you're wrong. Alright, so let's take a look at how we can do that. Okay, well, we've got e to the x minus 4. Okay, so I did take it easy on here, and we only have one modification to the graph, but still, the same basic thing holds true. I'm going to graph y equals e to the x to start with. Okay, now one thing you do have to kind of keep in mind is what e actually equals, but we're still just going to go with 1, 0, and negative 1. And remember, e is just basically 2.7-ish. And doing a graph by hand, 2.7 is more than enough decimals to get the point across. Okay, so anyway, as we do e to the first, that's still going to be 2.7. You know, e to the 0, well, anything to the 0 is still going to give us a 1. And then you'll have to do this at least once on your calculator probably, but if I type in e to the negative 1, I'm going to get some messy decimal. But that messy decimal, rounded to the nearest tenth, works out to be just 0.4. So really, those are the only numbers we need to be able to do this, just like we did the other ones. So now, looking at what's going on here, I've got this minus 4, which again affects me in the y direction, so I'm going to take the y column of my chart and add another one onto it, which we'll have a little d4 for down 4, and I'm just going to subtract 4 off all these guys. So 2.7 minus 4 is going to give me a negative 1.3. 1 minus 4 is negative 3. 0.4 minus 4 is going to be a negative 3.6. And then again, that makes that column useless. Okay, the negative 4 means my asymptote is down now at negative 4. Okay, my domain, as per usual, is going to be all reals, and then my range, again, since my asymptote's down at negative 4, and I'm going to be going up from there, although I'm a little ahead of myself, is going to be y greater than negative 4. Okay, now let's see if I'm actually knowing what I'm talking about. Down 4, 1, 2, 3, 4 is where my asymptote's going to live. That little line there, that was horrible. And, okay, now let's plot our points. I got 1, negative 1.3, down a little bit more than 1, 0, negative 3 puts me right about there, and then negative 1, negative 3.6 sends me a little bit more than halfway down to the negative 4 there. Alright, so again, you can get a little bit of that J shape going. So you can kind of see that I'll be flattening out over there, and then shooting nearly vertical again over there. So there's actually a very nice graph of an e to the x sort of thing by hand. Hoo-ah! Just loving it, aren't you? Alright, so let's get moving on to something that's non-graphical in nature. So you can say whew if you really need to. Alright, anyway, so if I'm solving equations, I've got this equation right here, which hopefully you're looking at that and going, yeah, 3. And it is. Okay, basically what's going on here, if I have 5 to some power equals 5 to some other power, well, pretty much it's got to be true that those powers have to match. So as soon as I see that, I can kind of think of the 5s canceling each other out effectively, and then you've got x plus 4 equals 7, and like I said a couple seconds ago, that gives me a 3. Okay, now what's going on here is an example of a certain property which mathematicians like to call the one-to-one property, which basically means if I've got some number to a power and I've got that exact same number to a different power, well, there's only one way to pull that off. So that's kind of what we just did there. I like to refer to it as the duh property, because that's exactly what it said. Hey, if those two things match, well, then the other two things have to match as well. So even if the base is some messy thing like e, as long as the bases match, well, hey, they just cancel each other out, and you're dealing with something like 5x plus 11 equals 76, which is pretty simple for us to solve. 5x, subtract the 11 gives me a 65, and then of course everybody knows 65 divided by 5 is 13. Okay, so again, very simple if the bases match. Unfortunately, of course, they won't always match. Okay, got a couple situations here where the bases aren't matching, so we have to do a little bit of work. Okay, now looking at 4 and 32, I have to ask myself, hey, what number raised to powers can give me both 4 and 32? Okay, you might think 4 initially, but I can't get 4 to 32 without using a fractional power, and I'd like to avoid that. So basically what I'm going to do is going to go lower here, and I know 4 is 2 squared, that's pretty simple, and then 32, well, hopefully that's something that at the very least, if you don't know it off the top of your head, you can figure it out in just a few seconds, and that's 2 to the 5th. So basically I'm going to replace the 4 with 2 squared, and that still has that x plus 6 on it, and likewise I'm going to replace the 32 with 2 to the 5th. He's still going to have an x minus 3 attached to him. And then of course the basic rule, if you have an exponent to an exponent, you have to multiply those exponents. So basically my left side here becomes 2, and then 2 times x plus 6 becomes a 2x plus 12, of course distributing there. Okay, likewise, the base 2 and then the 5th power to the x minus 3 power becomes a 5x minus 15. Alright, and of course the duh property takes over at that point, canceling out the 2's. And then so you're left with 2x plus 12 equals 5x minus 15. And I'm not going to insult your intelligence just to save time. I trust you can do that from there. Okay, same thing over here. We have a messier situation. I've got 5 and then I've got this fraction over here. Okay, well really remember all the fraction means is you've got a negative exponent going on. Okay, so well, let's see, 5 and 125. Hopefully you recognize 125 is 5 to the 3rd. So basically, because the negative exponent's involved here, in order to flip them over, basically that 125, or 1 over 125, is really 5 to the negative 3rd power. Okay, so what we can do with an equation like this, incorporating a negative to account for the fraction, is now we have 5 to the 6x equals 5 to the negative 3 to the 4th. Okay, again, a mild amount of cleaning that up gives me 5 to the negative 12th over there. Okay, and then again, duh, those 5's can drop out, and really, well, just because it's easier to write that than to write etc., you get x equals -2 very, very quickly that way. Again, just don't freak out when you see the fractions. It just means your exponent was negative. So figure out whatever gives you the denominator, and then slap a negative sign on it to account for the fraction part. Alrighty, one of the more common applications of these exponentials is in money, or more specifically in compound interest. Okay, and in order to pull off a problem like what we have here with 6,000 deposited 5% interest for 6 years, we need to have a formula that works with compound interest, and it's a fairly straightforward formula, but here it is. Okay, A is going to be our final amount. Okay, and then P is our principal, or starting amount, and then it's going to be times the quantity 1 plus R, and that's going to be our rate as a decimal, so make sure you convert the 5% into 0.05, and that's going to be over some letter N. That N stands for the number of years, or the number of times per year interest is compounded. Alright, so then our parenthesis closes, and then we have an exponent here, which is N times T. Okay, the N here is the same N as down below, number of times per year interest is compounded, and then T is the number of years. Okay, and so from there, if I'm interested in how much we're going to have if the interest is compounded annually, well, start filling in things here. A equals P, principal, which is our 6,000 we're starting with. Okay, and then that's going to be times 1 plus, okay, again, convert that interest rate into a decimal, so 0.05, all over N. Okay, now people tend to mess this one up, but if the interest is compounded annually, you have to ask yourself, how many years are there in a year? Well, I'm pretty sure there's only 1 year in a year. So that's what that is. Okay, and then of course I've got N times T, so I've got 1 times T, which is 6 in this case. Okay, and then again, if you can successfully punch that in your calculator, just be careful because it is a little bit messy. You should eventually get something like 8040.5, and then it's going to be 73, and since I'm talking about money, I'm going to keep that as a 7, not round it to a 3, up to a 8. Also, I'm going to go to 2 decimal places because it is money. So basically, at the end of 6 years, if you've got 6,000 bucks to throw in a bank, and you've got a 5% interest rate, which is actually really, really higher than most rates right now, that's how much you'd have after that 6 years. Okay, I'm not going to do all these because I know you don't want to sit here and watch it happen, but as soon as I'm talking about quarterly, well, how many quarters are there in a year? Well, that's going to be N equals 4, and other than that, everything else will be the same. You'll get a slightly different number at the end of it, but there you go. Of course, monthly, get you N equals 12. Now, continuously is a little bit strange. Continuously means that you're compounding interest every millisecond of every day, and that's, well, we don't have a number that big that we can actually plug in because that'd be kind of like having an infinity right here. Okay, but basically what that does is, through the magic of the number E, it actually spawns a slightly different formula that takes care of that sort of case for us. So A equals P is to start with, and then actually the number E takes over and ends up taking R times T power. I like to call it PERT. But anyway, that's the way you can do continuously. So if I have that same conditions, and I'm talking continuously, I've got A equals 6,000 principal, and I'm going to multiply that times E, and then 0.05, and it's a little awkward to put a dot over there, so I'm going to use a parenthesis with my 6. Okay, and again, just type that in your calculator, and whatever comes out should come out. But that's how you do it. Alright, and of course there's other types of word problems we can talk about with these exponential things, and one is population. Basic populations usually follow exponential curves, so here we go. Alright, so we got something here about Russia based on this formula here, and its population. Okay, now first question is the population increasing or decreasing? Okay, well, hopefully one thing you can actually do is, well, graph it, but hopefully even before you graph it, you can look at this exponent, and recognizing that it's a negative exponent means that, hey, I'm doing kind of a reciprocal sort of thing. And if I'm doing a reciprocal, it means I'm basically dividing. So increasing or decreasing, well, it's decreasing, because I know I'm definitely dividing. That is the best horizontal line I've ever drawn. Alright, so from there, again, if you wanted to, you could go ahead and graph this thing and play around with the window a little bit, and you should eventually get a graph that looks, something like that. Alright, so again, indicating that we have a decreasing sort of situation. Okay, now a follow-up question is, what's the population in 2003 according to the model? Okay, well, my model says that my population is 152.26 times E to the negative 0 point, etc. is 39. T, now the question is, what is T in this case? Well, I want 2003. Okay, now T equals 6 corresponds to 1996. Now that's maybe a little awkward. So if your brain hurts from looking at that, well, just back everything off 6 years, and that means that T equals 0 corresponds to 1990. And then maybe that's a little easier to figure out that 2003 is now T equals 13. Okay, so now by plugging in a 13 up here and correctly typing things in my calculator, I should get a population of 144.7 and then some other stuff, but let's just round to the nearest tenth for now. Okay, so does that mean there was 144 people in Russia? No, of course not, because that's population in millions. So basically what we've got here is 144.7 million people. Okay, and you've probably been staring at that thing in the lower right corner. I'll leave it to you to either figure it out or ask me about it tomorrow. Alright, see you guys in class.